Hello my dear friends and welcome again to Adventure Story channel video. Today my dear friends we will continue our training course of LNG vessels. First of all, I'd like to thank you that you have stayed tuned and you have watched the previous videos. Thank you also that you comment on the videos. This is very interesting. And also I have some questions if I have changed from tanker ships to LNG. Not for the moment I have not changed, but the interesting thing is that these vessels are in some kind of have similarities because they carry both products which is from the crust of the earth, and it's very interesting to fill our knowledge to make it more specified and more interesting, so we can be more flexible in our daily work schedules. And with this knowledge our mind it's only sure that we'll be more flexible and we'll see with different way the things. First of all, let's begin our lesson again, our training course, and I will start from there we have finished. So I will press again the button, so we have the description of the molecules and we will see the movement, how they interact with each other.
A gas, refrigeration and liquefaction of gases. A gas is a collection of molecules flying around in space. If we were to add up the volume of each individual molecule, it would be quite insufficient to fill the space which contains them. As the physicist Oliver Lodge summed it up, a gas is something in chaotic movement, which is bounded by the surfaces of the container around it. In fact, the very word gas comes from the Greek for chaos. Within a container, we can think of gas molecules or atoms as balls, bouncing off each other and off the surface of the container. Their speed of movement depends on the energy level or temperature of the gas. As we cool the gas down, the speed decreases, and eventually the molecules will stick together so that the gas becomes a liquid. This liquid is bounded by the lower surfaces of its container, but the upper surface reflects gravitational attraction.
So we have a description of these gases. Also, gases can formulate it in the tanker vessels, on the surface, on the top. So also it interacts with the temperature. As the temperature decreases, there is a less pressure production inside the tanks, and as the temperature increases, we can see the pressure inside the tanks to be increased, because due to expansion and due to more movements of these molecules. So let's continue next.
So, by condensing a volume of gas and turning it into a liquid, we can reduce its volume many hundreds of times. This is the basis of transporting gases in liquid form. For example, propane gas occupies approximately 250 times the volume of propane liquid at 15 degrees Celsius. The ratio of gas to liquid volume for LNG is about 600 to 1.
So we can confirm the volume, how much it will be reduced as the gas is cooling down.
Once natural gas has been extracted from its underground reservoir, it then has to be processed and prepared for transportation. The processing consists of removing the heavier hydrocarbons and non-hydrocarbon constituents to produce natural gas that is fit for liquefaction or use as a fuel. Some of the ethane, propane, butane and pentanes that have been removed may be used elsewhere. Known as natural gas liquids, NGLs, they are valuable byproducts of natural gas processing. NGLs include ethane, propane, butane, isobutane, and natural gasoline. These NGLs are sold separately and have a variety of different uses, including enhancing oil recovery in oil wells, providing raw materials for oil refineries or petrochemical plants, and as sources of energy.
So we have seen after natural gas has been extracted, we see how the processing take place, where they use, and let's continue to another page.
This LNG liquefaction plant is one of the most common in use today. The system uses refrigeration by mixing cooling fluids and pre-cooling with propane. The process utilizes two cooling circuits. The first uses propane as a cooling fluid, and the second a mixture of ethanol, propane, methanol, and nitrogen. The composition of the mixture of coolants is based on the composition of natural gas in the plant. After passing through the pre-treatment systems, the natural gas is cooled in a propane vaporizer. The pressure of the propane is adjusted to maintain the least possible temperature in the natural gas, so as to avoid condensation. The gas then enters the main cryogenic interchange, which cools the natural gas through a closed circuit of mixed coolants. The current of refrigerants is cooled at the compressor's exit using seawater, and then by propane in evaporators with high, medium, and low temperature.
So we can see that we have this liquefaction plant, which stage by stage will cool down the gases. And then, so by cooling down, we'll reduce all this volume as much as possible, and will be more easy to transport all these liquefied gases.
After liquefying the natural gas, it is subcooled and stored. The liquefied natural gas is partially subcooled so that it produces the least amount of vapor in the tank filler, followed by an expansion to a slightly higher pressure than atmospheric. The flash gas generated during the expansion, together with the gas coming from the evaporation in the tanks, is used as fuel for the plant's gas turbines. Subcooling involves cooling the liquefied natural gas to below the saturation temperature. By their very nature, refrigerants must be volatile substances. The liquid is nearly always at a balanced, saturated state with any vapor present. When the liquefied natural gas loses any pressure or gains any temperature, some of it will be flashed to vapor to reach a new balance. There must be a higher pressure upon entry into the liquid line than at its exit. Otherwise it will not move in the line. This inherent pressure drop always creates flash gas, no matter how much liquid is available at the start of the line. This is aggravated by friction losses, fitting restrictions, and any rises in elevation.
So let's continue to the next page.
Critical temperature. When we are handling gases on board ship, we need to consider not just the temperature, but also the volume and pressure. These define the total heat content of the gas, or its enthalpy. In our example of water, we know that the transition temperatures, the freezing and boiling points, are 0 degrees Celsius and 100 degrees Celsius respectively at atmospheric pressure. But these temperatures can be altered by changes in pressure. For instance, on board ship, we often reduce the pressure and then boil seawater to distill it and obtain fresh water at jacket water temperatures. Conversely, in steam boilers or autoclaves, the pressure is increased and the boiling point is raised. Furthermore, the latent heat of vaporization varies according to whether the boiling is being undertaken at reduced or increased pressure.
So there is a lot of information that we need to know, that is sure. Always take your time to adopt and understand what is talking about, it's really important to see that parameters. So let's move on to the next page.
When the relationships of enthalpy against pressure are plotted on a chart, the resulting diagram is known as a Mallya chart. This is an essential aid to understanding what may happen when we liquefy or condense cargo gases. A simplified version of a Mallya chart is shown. The diagram plots the enthalpy along the x-axis and the absolute pressure on the y-axis. From the bottom left, a curved line runs up towards the right, levels off, and then turns down again to the x-axis. The left-hand portion of the line represents the saturated liquid line, and the right-hand portion the saturated vapor line. In the region between and below these curves, there is a mixture of liquid and vapor. The transition point at the top is called the critical point. The horizontal distance between the curves denotes the latent heat at a particular pressure, and this decreases as the pressure increases until, at the critical point, it becomes zero.
So this Mallya diagram, it's really important. We use also when we take the second engineer license. Also in the academy you will be teach this diagram. It's really important, and for each gas there is a different kind of Mallya diagram, that is sure. So here you can see what is going on, the latent heats. You can see the condition that your gas is, it's liquid or vapor. There is a lot of information. There is pressure information, what is going on, the pressure, the absolute pressure, and the enthalpy down on the x-axis. So this Mallya diagram, it's really important to know and to handle also. So let's move on.
The other lines shown within the envelope run through points with the same dryness fraction. The figures show the fraction of gas in the mixture. That is, 0.4 means that 40% of the mixture is liquid and 60% gas. To the left of the saturated liquid line, there will be subcooled liquid, and to the right of the saturated vapor line will be superheated vapor. The dashed lines are lines of constant temperature, and by looking at these, it is clear that at a certain temperature, the critical temperature, it is not possible to liquefy the gas, no matter how much the pressure is increased. The gas must first be cooled to the critical temperature or below.
So with all that Mallya diagram, we can see the state of the gases and what we need to do so to achieve the liquid phase. As you can see in the critical point, as much the temperature increases, there is no way to make our gas liquid. We need to go down below to the state to cool down and change the state also. As you can see, there is a lot of parameters. As we can see here, 0.4 means, and this is very important to remember, that 40% of the mixture is liquid and 60% is gas. Also here on 0.6 means that 60% of mixture is liquid and 40% of gas. As we go here, 0.8, 80% of mixture is liquid and 20% is gas. Correct? If I'm not correct, make it in your comment. Also, this is really important to remember this equation, which one is. So this is a representative Mallya diagram. Maybe you will have on board the vessel or you will have somewhere a more better diagram, and we can look for that in other video. So we have also the enthalpy description more clear, and we have more details for specific gas. I will try to find some kind of Mallya diagram which we can see more details and understand more specified. So in basic, you need to know that there is some kind of this diagram, Mallya diagram, which shows a lot of details about the states, the pressures, the enthalpy, and the condition of the gas, how much liquid and how much gas it is, that of temperature and pressure. So let's move on.
As the diagram shows, for some of the cargoes commonly carried, such as ethylene and ethane, this critical temperature is in the ambient range. For LNG, it is well below this.
So we have all the gases here. We have saturated vapor pressure and also temperature. As we can see, methane going more cooling after going ethylene, hottest, and butane, butylene, vinyl chloride, ammonia, propane are close to zero. So we have the absolute pressure and the temperature, and we have a comparison of different kind of gases. Let's move on.
Diffusion and mixing of gases. Diffusion is defined as the spreading out of a substance from a concentrated source, which results in an increase in the entropy, degree of disorder, of the substance. Diffusion occurs because of the random movement of molecules of the substance, which allows them to separate from one another. The greater the space between these molecules, the greater their ability to spread out from one another. The more densely packed the molecules are in the substance, the less space there is to maneuver, and therefore the more difficult it is for diffusion to occur. Solids, for example, are composed of very tightly packed particles, and so any diffusion occurs extremely slowly. If a lead brick and a gold brick were wrapped together in close contact, it would take several years before the two bricks were glued together. The atoms are able to diffuse into each other's solid matrix, causing them to adhere to one another, but only after several years of contact with each other's surface.
Very interesting to see that about the diffusion, how the molecules interact together, and as more solid, it's more difficult. As you heard, it take a lot of years. It's really interesting to hear that. And also, the greater the space between the molecules, the greater their ability to spread out from one to another.
On the other hand, liquids consist of particles that are less closely packed and which can move more freely. Any diffusion is likely to occur at a faster rate. If a drop of colored ink is placed in a glass of water, the molecules of ink can diffuse fairly rapidly between the water molecules, so that the water becomes evenly colored by the ink in a matter of minutes.
Very, very nice to see an example here. So I will click here on, and we will see how the diffusion take place. Yes, because the distances between the molecules is very, very far, so the diffusion will be more faster.
Gaseous substances are in a different league again. The gas molecules are much more distant from one another than is the case in liquids or solids. That is why gases are transparent. Light can pass through the relatively large spaces between the gas molecules without any distortion. If a gas with an odor, such as ammonia, is released from an open bottle, it will take only a few seconds for the odor to be detected throughout the room, as the ammonia molecules rapidly diffuse through the air. The speed or rate of diffusion is also affected by the mass of the particles. The heavier a gas, the slower its molecules will be able to move. The relationship between the rate of diffusion of a gas and its molecular mass was investigated by Professor Graham. He found that the rate of diffusion was inversely proportional to the square root of the molecular mass.
Very interesting to see that. Okay, start diffusion. It will be really fast, and the rate of diffusion was inversely proportional to the square root of the molecular mass. So here we are. We have finished all the section, and you're about to start the test for this unit. Click Start button to begin the test, or the back button to view the unit again. So I will take the test, and you will be here to check also with me the results. So volume, when one volume of liquefied gas LNG evaporates, roughly how many volume of gas will be produced? I will answer 600. Next. What is the term used to define the total heat content of gas? Total heat content of gas. It is enthalpy. So, is the state about liquid cargos true or false? Is the state of liquid cargos true or false? The pressure exerted by boiling liquid vapor of gas within a closed container at a given temperature is known as SVP. The pressure exerted by boiling liquid vapor of gas within a closed container at a given temperature is known vapor pressure, saturated vapor pressure. Okay, we'll answer true. True or false? The critical temperature of methane is the ambient range. The critical temperature critical temperature for is in ambient range. I will answer false because I have seen methane was minus, is in the ambient range, but in the questions was answering that it's on the ambient range. So a gas cannot be liquefied if its temperature is above critical. Yes, it's true. A Mallya chart is used to understand what may happen when cargos gases are liquefied or condensed. Which property does Mallya chart plot? Okay, it's a plot enthalpy and absolute pressure. Enthalpy and absolute pressure, yes, correct. What is the principal consignate of LNG? Methane. Methane, LNG, cannot be liquefied by pressure alone and must be carried at its atmospheric boiler approximately minus 160. So let's see. I make one mistake. I like to review all the answers. Was false. Okay. The critical temperature for methane is ambient range. No, it's not on the ambient range. So this was my mistake, and I believe it is nice also. I believe it's not so bad. That seems that these tests really helps. So I will go to main menu. We have finished fundamental knowledge and understanding only physics and chemistry. There is a lot of things here. Awareness and main design principle.
In order to carry low temperature liquefied gases, it is necessary to bear in mind that most metals lose their ductile strength and become brittle when cooled below a certain point. The temperature at which a metal becomes brittle depends on the composition of the alloy, and how it has been heat treated or prepared. For cargoes below -55 degrees Celsius, the materials that are still ductile are nickel alloy steels, austenitic stainless steels, or aluminium alloys. The principles which govern the cargo containment system on LNG carriers are based on the regulations in the various gas codes. See Section 1.3. The aim is to ensure that any risk to the ship, its crew, or the environment is minimized. This is generally achieved, in terms of construction, by fitting the ships with a complete inner hull, or secondary containment barrier, in case a leak should develop in the cargo tanks. This will prevent any of the extremely cold liquid reaching the outer hull, as this would be seriously weakened by such an occurrence and brittle fracture could result.
So we can see here how important is to be awareness of the main design, how it must be properly take care by the regulations. And if such thing can occur, just imagine what damages can it make for the hull structure and how it can produce any other damages to the vessel also itself, if it's traveling in the rough sea or something else. So let's see also this section today. Let's place these buttons. -5 to carry full refrigerant butane, -55 to carry full refrigerant C3S. This is also the special practical minimum temperature you can reach with special steel alloys. -105 to carry full refrigerant ethylene, 165 to carry LNG, 196 for system use with liquid nitrogen, mostly inner gas systems.
Various types of tank system have been developed to meet these requirements, and these will be considered in more detail in Module 2. Leak detection and alarm systems are also required. Damage survival requirements are also a major feature of the gas code. Gas carriers must be able to withstand a far greater degree of damage than an oil tanker. The intent is that the ship should survive flooding after hull damage caused by an external force. Measures could then be taken to salvage the cargo or the ship, or to remove the danger to the surrounding area by other means. Cargo tanks must also be located a specified distance inboard from the hull to protect them from minor damage, such as contact with a tug or jetty, or from the effects of collision or stranding. More details may be found in the next unit.
Very, very interesting. Also in the previous page I was thinking that for sure there must be fitted some kind of system, detection system, alarm system, which notify the personnel who involved on these operations that there is some kind of leakage or some alarm which show how much serious is the leakage or the damage on the hull or some compartment or the cargo tanks or cargo holds. So I will go back to menu, fundamental knowledge, okay, principle of design. We have awareness and made design. Let's check
in order to carry various types
that. And okay, on the end we have a test. Okay, we will start the test. Is the state about the carriage of liquid cargoes true or false? Milled steel will not affect it by leakage or cold liquefied gas. Milled steel for sure will be affected, so we will press false because milled steel is not so strong material. We need some special alloys, as we have seen previously. and only that special alloys, which includes nickel, will withstand, or some different kind of materials will withstand these conditions. So the secondary barrier is intended to retain the cargo and protect the hull from the brittle structure in the event of tank failure. Yes, must be always second barrier to retain the cargo, yes. And what is the practical minimum temperature that special steel alloys can reach before they became brittle? It's the minus 55 degrees Celsius. That is true. So we have learned a lot of things today. We will make a pause on this video and we will continue on the next chapter later. So as you can see, the LNG tankers have much more protection than tankers, because as we know, if something happened, there is some kind of 10 bombs like was dropped in Nagasaki and Hiroshima. So just imagine how much damage can achieve from this kind of ships, and for sure the security and the safety for this kind of ships must be increased as much as possible, and all the factors and all the risk will be eliminated from the beginning, from the construction of the ship. The proper way of building the ships and the regulations will be more easier to apply, as we have seen on the video about ergonomics, which I have made also, which improves everything, the safety, also protect the personnel, minimize the risks, and this is the good thing. So let's see our results here. Let's see that we have 100%. We can print, or we will continue next to the knowledge and main design principles later. So my dear friends, thank you that you have watched this video. I'm really like when you interact and you watch the videos, and I hope you every day learn something interesting, which will drives you a step forward on the knowledge and the proper application of the regulations and the rules in this shipping industry, which by the future will be more competitive from the view of knowledge than the engineering applying. But combine two of them, you will achieve a good standard and you will be competitive on board the vessel and through the time you're on board. Thank you, my dear friends. Don't forget to check the playlist, don't forget to subscribe and to press button. Always your comments are welcome here. See you in the next video. Bye bye.